Hello everyone, and welcome to this very new video which we are making as part of a Diwali series. In this video, I'm going to be solving a question which is in essence an application of the Euler's Polyhedra theorem applied to planar geometry. Now, the concept of Euler's Polyhedra theorem applied to planar geometry, I had discussed in an earlier video as part of our Navratri's set of videos. So I'm going to link that video in the description of this one. If you have not watched that video, I would definitely encourage all of you to go and watch that video where we have derived a formula. And this question that we're going to be solving today is going to require the usage of the formula to get to the correct answer. So everyone who has not watched that video, please go and watch that video first, and then you will find your appreciation for this video a bit more. So let's look at the question that I have actually posed for this video. But before that, let me once again quickly recap the formula for Euler's Polyhedra theorem applied in planar geometry that I had derived in the previous video. So the formula that I derived is that n minus s plus a is equal to 1, where n is the number of nodes. Now, what are nodes? Nodes are the end points, the starting and the ending points of line segments. S is the number of line segments or number of sides. Sides are defined as the line segments which are present between any two nodes, and A is the number of isolated enclosed areas. So what we had derived is that if I have, say, a random graph, a random planar graph in which several different straight lines are drawn like this, then each of the points at which different line segments are having the starting and ending point will be called the node. So this is a node, this is a node, this is a node. Each of the line segments is called a side. And the number of enclosed areas, for example, this is an enclosed area, this is an enclosed area, this is a number of enclosed areas. These three are related by a formula, n minus s plus a is equal to 1. So using this particular formula that we had derived in the last video, let's solve a simple question. Let's have a look at the question very quickly. The question asks us or says that consider endpoints, no three of which are collinear on a plane. So no 3 points are collinear, all the points are non-collinear, which means that if I select any 2 points among these endpoints, I will get a distinct straight line, right? And then the question says that each of these points are joined by a straight line segment with every other point. So which means that if I have, say, 6 points, then every point is joined using a straight line segment to the remaining 5 points, right? And the straight lines which are formed by this particular operation, no 3 of them are concurrent. Concurrent means no 3 of them intersect at the same point, which means every pair of straight lines or line segments so formed will intersect at a distinct point. And we have to find out how many individual enclosed areas are there in the figure thus formed. So if the question is clear, it should also become very clear why we will apply the Euler's theorem that we had derived. Because in this particular theorem, if I can find out the value of n, and if I can find out the value of s, then a is what I have to find out, because they're asking us how many individual enclosed areas are there, right? So s is the number of sides or the number of line segments which are present between any two nodes. N is the number of nodes, which means it is the endpoints of any line segment. So all of this, both of this, if I can say find out or calculate, if I can calculate n and s for this particular question, I can find out a by solving this particular equation. So that is how we are going to be solving this question. So if this question statement is clear, let's first try to understand how to calculate the number of nodes. So number of nodes, first part is very easy because we are beginning with endpoints, and each of these endpoints will be a node because with each of these points, we are joining every other point. So we will have several different line segments with these nodes at the starting or the ending points. So which means I have got n nodes here. Apart from these n nodes, we will also have a node at the point of intersection of any two line segments, right? So if I have got two line segments intersecting at a point, even that point of intersection will be a node. So how many points of intersection will be there? That also needs to be calculated, and that needs to be present as part of a calculation of number of nodes. Now, how do I calculate how many points of intersections are there? For that, we have to understand that intersections can only be formed when I have got two line segments. And we know that to form one line segment, I need two nodes, which means to form two line segments, I will need 4 nodes. And because we have been told that all the points that we begin with are completely non-collinear, no 3 of them are collinear at all, which means if I pick up any 4 of these endpoints, I will get 4 points which are not on a straight line. So if I join all those 4, I will get a quadrilateral. So using any 4 of these n non-collinear points, we will get a quadrilateral. And we know that inside a quadrilateral, there will be only one point of intersection of diagonals, right? So just to give an example, if I've got 4 such points, Then if I select these 4 points, only one single quadrilateral can be formed using these 4 points. And inside this quadrilateral, if I join every node with every other node, I will get 2 diagonals, and the 2 diagonals will intersect at only 1 point. So there will be only 1 point of intersection within each and every quadrilateral. So how many points of intersection will be there when there are n nodes? Will be equal to the number of quadrilaterals that I can form. Because for every quadrilateral, there will be one single point of intersection inside it. If this is clear, then we should know that the number of quadrilaterals that I can form using n non-collinear points will be NC4. So these NC4 quadrilaterals will have NC4 more nodes, which means that n plus NC4 will become the total number of nodes in our question. So this will be equal to n. So the value of n we have already calculated. Next, let's try to find the number of edges or the number of sides or the number of straight line segments between any two nodes. So for that, first, let's only consider the initial n nodes that we begin with. So using these initial n nodes, so the total number of line segments that I can form is going to be NC2, because if I join any two of these nodes, I will get one straight line segment. So NC2 will be the total number of line segments that I can form using this, the initial endpoints. But we also have to understand that the edges, that will be more number of edges that is going to be formed with starting or ending point as a node which is formed by the points of intersection. So for example, again, if I look at this quadrilateral, then there are 4 sides. So these 4 sides I can calculate using 4C2, right? In fact, I can calculate this also, right? These 2 diagonals, all of this will be included inside 4C2. But because I have a node here, so then there are actually more number of edges which are being formed. So how many edges are being formed because of the nodes which are present at the point of intersection, excuse me, of 2 straight lines? That also needs to be found out. Now, how will I find out that? For that, I have to understand that every single node will divide or will produce 2 more lines. Right? For example, these 2 diagonals were there. But if I consider this point of intersection of the 2 diagonals as a node, now I have got 4 line segments. Similarly, if I have got, say, 3 lines which are cutting each other, then to begin with, I have got 3 lines. But this node is going to give me 1, 2, 3, 4 line segments. And this node is going to give me 1, 2, 3 more line segments. So which means in total now, I have got 1, 2, 3, 4, 5, 6, 7 nodes. So which means that from total of 3 lines, we went to a total of 7 lines. From a total of 3 edges, we went to a total of 7 edges because of 2 nodes. Why? Because every node is giving me 2 extra straight lines or 2 extra edges. Similarly, if I have got 4 nodes, then or 4 straight lines which have got points of intersection as 4 different nodes here, then initially we have got 4 edges from which we are going to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So, and 12. So from 4, we are going to 12. Why? Because every single node is making 2 extra line segments. So for every single node which is present at the point of intersection of 2 lines, I will get 2 extra line segments being produced because of that. So which means the number of edges which are being formed because of the intersection nodes will be number of intersection nodes multiplied by 2. So 2 into NC4 more nodes I will be able to form apart from the NC2 line segments that are being formed by joining any 2 points which were initially given. So which means the total number of edges will be 2 into NC4 plus NC2. So this will then be equal to S. So now we have the value of N, we have the value of S. Now if we apply Euler's Polyhedra theorem in planar geometry, then solving this equation, we can find out the value of A. So plugging in the value of N as NC4 plus N and plugging in the value of S as 2 into NC4 plus NC2, I can get the value of A as 1 minus NC4 plus N minus 2 into NC4 plus NC2. Using this, we can always calculate the number of individual areas that are being formed whenever we have got n non-collinear points in a plane and all of these points are being joined with all of the other points. Let us apply this in a couple of specific cases and see whether we are getting to the correct answers or not. So for that, let's take the case of a quadrilateral. So I have a quadrilateral, which means I was given only initially these 4 points, A, B, C, and D. So when I'm joining A with the remaining 3 points, B with the remaining 3 points, C with the remaining 3 points, and D with the remaining 3 points, and this is the total figure that I will get. So now I will get the value of A as 1 minus NC4 plus N minus 2 into NC4 plus NC2. So I will substitute N as 4 because I began with N nodes. Right? So when I do that, then the number of nodes that I get is 4C4 plus 4. Now 4C4 is 1 and 4 is 4. So I should have 5 number of nodes. Let's see if that is true or not. So I've got 1, 2, 3, 4, 5 nodes. So that calculation is absolutely correct. Now let's see how many different line segments I will get, or how many different edges I will get. Using the formula that I've calculated, it is 2 into 4C4 plus 4C2. The 4C4 is 1, 4C2 is 6. So 2 into 1 is 2 plus 6 is 8. So am I getting 8 different line segments? Let's check that. AD, CD, BC, AB, and if I call this point of intersection node as E, then AE, DE, CE, BE. I have got 8 edges as well. So both these calculations are correct. So using the formula, then I will get 1 minus 8, or sorry, 1 minus 5 minus 8, which is 1 plus 3, which is equal to 4. So I should have 4 isolated individual enclosed areas. So am I getting that? I'm absolutely getting that because I've got one area here, second area here, third area here, and fourth area here. So clearly our derived formula is giving us a correct answer. Let's try to apply this in the case of 5 points as well. So if I've got 5 points, A, B, C, D, E, and D, and I join every single point with every other point, then this is a figure that I'll get. So again, applying Euler's polyhedra theorem for planar geometry and substituting N as 5. This is the equation that I will get. Now again, let's calculate the number of nodes. Number of nodes is 5C4 plus 5. 5C4 is 5. So 5 plus 5, 10 should be the value of N, should be the number of nodes. So let's calculate if there is 10 nodes or not. So I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm getting 10 here. And then the number of edges is 2 into 5C4 plus 5C2. Now 5C4 is 5 and 5C2 is 10. So 2 into 5, 10 plus 10, 20 different edges I should get. So let's see if I'm getting 20 edges or not. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 edges I'm getting, which means that even the calculation of E according to our formula is absolutely correct. And if I simplify this, I get 1 plus 10, 11 to be the total number of individual enclosed areas. So let's see, let's count and see whether 11 is the correct answer or not. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I get 11 individual enclosed areas. So this is how we can apply the concept of Euler's polyhedra theorem in planar geometry to solve questions which are at the confluence of geometry and permutations, combinations, and probability. Hope all of you enjoyed this particular concept. If yes, then please click the like button, and thank you for watching the video. And a very, very happy Diwali to all of you from Team GradSquare. Take care.